This is the 4 or 5 notes for Calculus 1. We once again are going to be tackling another application of derivatives, this time called optimization. Optimization basically is the attempt to find the most efficient way to carry out a task. So this could be a variety of different contexts. It could be least expensive, most profitable, least time consuming. It could go. There's a variety of different genres of type of optimization problem, but very important problem nonetheless. You'll see it a lot in business applications, among other topics. It says, let's start with a simple and just think of two non-negative real numbers. So in your head. And just assume that the sum of these two non-negative real numbers is 20. So remember, real numbers can be integers or decimals. Whole numbers or decimals. So just not negative, right? Because we want to make sure that they're non-negative. It says, of these pairs of numbers, which has the greatest product? What is that product? Okay, so this is the important question that our optimization problem is aiming to answer. Of the pair of numbers whose sum is 20, what has the absolute greatest product? Okay, so let's talk about what we know. So let's say we define the two non-negative numbers as x and y. Okay, those are our two numbers. What do we know about their sum? Well, we can state that for sure we know that x plus y is equal to 20. Okay, we refer to that as the constraint of our optimization problem. Why is it called that? Because we are limited to this fact that x plus y must be equal to 20, so hence the term constraint. Okay, the quantity that we actually wish to maximize or minimize in any case is called the objective function. Okay, so in this case, what are we trying to find? We're trying to find the one with the greatest product. So we're trying to basically maximize what the product could possibly be. So if you look closely, all we need is, we usually state whatever the variable is that we're trying to find, which is P for product we'll use, right? And then what is the product equal to? Well, clearly it's going to be equal to the multiplying the product of x and y. So that means our objective function is that. So some of the interesting observations to be made, the constraint usually has some type of number value that you're limited to in the problem, while the objective function is more about just a strict formula that you're trying to maximize. So before we talk about the calculus way to do this, let's talk about how we would, in our regular lives, try to figure this out. Just a logic problem. Forget about calculus for a second. So what I did was I went through and I looked at some possible combinations of x and y and what you get as their product. So clearly, I have 5 different combinations of x and y's whose all sum is 20. So that's the constraint in our problem, right? This is our constraint. And we are trying to find the highest, the greatest product. So let's say we have 1 and 19. Clearly a sum of 20. What's their product? It's 19. Okay, moving on. So let's say we have 5.5 and 14.5. So these are legal numbers. They are real numbers that do have a sum of 20. If we take their product, a simple calculator look at this, it'll be 79.75. So if this is, let's say, a race to find the greatest product, basically, who's winning? Well, it looks like so far 5.5 and 14.5 has the higher product. Okay? Now, what if we went to the next one? So let's say we went a little bit closer together. We went to 9 and 11. So then we go 9 and 11 makes 99. So far we have 9 and 11 kind of winning the race. So why don't we pick a couple other ones just for argument's sake? So we'll pick 13 and 7, which is a product of 91, 18 and 2, which is a product of 36. So far the middle one over here seems to be the one that is winning because it has the greatest product. So hopefully you can kind of make an observation that's happening here. So the numbers that are farther away from each other on the outside seem to be the smaller product. So it appears that as we get closer, the numbers get closer to one another, we seem to get a larger product. So we can kind of make that sort of guess on what this is going to do. And I'm sure that you guys all know what the two numbers are if you just do a little bit of thinking there. We'll talk about that in a second when we use calculus. Okay, if we want to be super technical, this is what we're actually trying to find. We're looking for what pair of non-negative numbers maximizes p equals xy subject to the constraint x plus y equals 20. This is the question that we're trying to ask. Do you have to memorize that, how to say that, or anything? No. But generally, and more technically, that is exactly what we need to find. So let's start to bring it towards what we would have to do in an example in terms of algebra and pre-calculus. Okay, so how do we solve these problems? Right here. It says the first step is to always use the constraint to express the objective function in terms of a single variable. Okay, so here's your objective function. But what we want to do is we want to end up with an equation p is equal to something with only one variable. We don't want two variables on the right side. We only want one. So the goal is we need to use the constraint in order to turn that equation into a one variable equation, essentially. So how do we do that? Well, here's your equation. Here's your constraint. Let's solve for y and get y equals 20 minus x. So what we have is essentially now a system. We have, as I said before, so we have this formula here, but we also have this here. So if you look closely, wherever we see y, we should be able to put 20 minus x. So if we do so, we're going to leave the x, which is here, but then we're going to replace the y with 20 minus x. If we do so, we can distribute and get 20x minus x squared. Okay, so this equation right here, this y equal, or p equals 20x minus x squared, I'm going to rewrite it just for argument. P is equal to 20x minus x squared. Boy, that's colorful. This is essentially our new version of our objective function. This is the function that not only takes into account that we need a product, but it also takes into account the objective function. So that of our original, it takes into account objective function and the constraint. So this formula is what we're going to move on to because now we can apply the calculus. So if you look over at the right side right now, you'll see basically the equation of our function. So remember 20x minus x squared, which we got right here. Ooh, highlighter. 20x minus x squared. So that is this function right here. Upside down parabola. Makes sense. So what do we need to do in order to maximize, find the numbers that will create the greatest product? Well, just note, basically this is the product right now, which is p. Okay? We're down here, this is basically going to be our value of x. Okay? Our value of x, which is, in our problem, is going to be, just from our sort of understanding process, is going to be our first number. So, what do? Well, remember, if we want the greatest product, what are we looking for? We're actually looking for this point up here. Well, hopefully you guys remember that that is going to be your local max. And when we had to determine our local max, what did we have to do? We always had to first set our derivative equal to 0. Well, now we have our equation that we can find the derivative of. So how do we do something like that? Well, I'm going to change this equation to p of x. So we're going to call it p of x. So therefore, we can do p prime of x is equal to the derivative 20x is 20 Derivative of x squared is 2x. So what we just did was we just found the equation that represents the slope of the tangent line. So this is the slope of the tangent line at any point. So if we're looking at this guy right here, we want to know when the, you ready? Slope of the tangent line is 0. So again, we want to know when it creates a tangent line with slope 0. So we have to set 20 minus 2x equal to 0 and solve. And get x is equal to 10. Okay, so what did we just find? This is essentially our critical point right here. So, but it also is the first number. It's the optimized value of x. So our first number of what we're going to do in order to create our product is 10. Well, just to be clear, look at our first numbers here. We didn't have a 10 in here, did we? We had 1, 5.5, 9. 9 was the closest we got. So we have now learned that 10 is the most optimized ideal number for finding the greatest product. So what do we need to do? We need to find the value of y as well. So how do we do that? We use our constraint right here, which we already solved to get y equals 20 minus x. So we're going to do y equals 20 minus our 10 to get 10 as our value of y. So clearly, if 9 and 11 make 99, 10 and 10 make 100. So that is the highest product you can possibly get. You can also find that product by simply subbing the number 10 into our equation over here. You're going to get 200 minus 100, which is 100. So just as a summary, it says right here, we can clearly see on the graph that the function p moves along its interval of interest. I'll define this in a second. 0 to 20. So 0 to 20. That the absolute maximum or optimized value is at 100 when x equals y equals 10. That is our product. So what would the question normally ask? It's the same thing. What did they ask? They asked for what is the greatest product, which was here, right? Greatest product. And then what is that product? Well, our greatest product was created by the numbers 10 and 10. And that product is 100. So that would be basically the answer to our problem. Okay, so this is going to be for MyMathLab, okay, only. So I'm going to stick to that. So you see that MyMathLab actually has this concept called interval of interest. I've actually never seen it in any other textbook, believe it or not. So I can't give you homework problems that ignore this concept, or I would. But it's not that it's not useful. It's just it is good for thinking process of it, but I normally wouldn't include it. But because the only problems I can give you have it, I'm going to show you what it means. All it is the possible values of x that your problem can possibly take. So as you see here, in this problem, our x values can only go from 0 to 20. That is your interval of interest. Now, the problem is that we don't normally have a graph to look at. We normally have to do this entire process without a graph. So, how can we do this without a graph? That's the key. All you have to do is you take your original equation and you set it equal to 0. So here we go, right here. You set your original equation to 0. You solve for all the possible values of x, and usually those values of x are going to be 0 to a specific number. So this isn't too important. It's this number is going to be your end value for your possible values of x. So your interval that they would be looking for would be 0 to 20, which is basically the answer to the MyMathLab problem. So this is just an aside to sort of help you answer those. And I will touch on that when I do some of the example problems. I usually do it sort of at the end just because I just want to do the problem, and then I'll show you how MyMathLab would deal with it. All right, so let's get optimizing now that you have a basic example out of the way. says a rectangle has a perimeter of 80 centimeters. Find the dimensions of the rectangle and its maximum possible area. So whenever you see maximum or minimum possible, then you're dealing with an optimization problem. So it's not going to use usually the word optimization, so you have to be on the lookout for those terms in a word problem. So what does this look like? So what do we normally do in these problems in the beginning? So we first came up with our constraint and our objective function. Okay, so in this problem, let's draw the picture. So we have a rectangle. We know that the perimeter of that rectangle is 80 centimeters. Okay, a rectangle has variable dimensions. Makes sense. So what are the dimensions? We'll call this x and we'll call this y. So right now we are essentially constrained, and by the way, don't get confused by P again. The P for product and P for perimeter, two different things. Just so happens it's a coincidence we're using the same capital letter P. We'll actually use some other variables in a second. So what's the first thing we need to do? We need to find our constraint. So we are right now limited to a rectangle that has a perimeter of 80. So what kind of formula does perimeter come up with? Well, we know that this is true in a rectangle. So right now we know that 2x plus 2y is equal to 80. So this is essentially our constraint. This is our x and y values must absolutely fit this. We can also reduce by dividing everything by 2, and this would be essentially our constraint. Okay, now what are we trying to maximize? We're trying to maximize area. So we need a formula for our objective function. So area in a rectangle is equal to x times y. So this is going to be our beginning objective function. All right, but what do we basically have? We have two equations here, right? So those equations, let me do it in a different color. So those equations are a part of a system. And the goal is that we need to use our constraint to limit this to only one variable. So this is very much like the problem that we did before. So how do we do that exactly? Well, we're going to take this and we're going to solve for y. I like to use x as a variable just because most students are comfortable with it. So therefore, we can then take our 40 minus x and we can place it wherever we see y in our problem. So we then can put these together and we're going to get a is equal to the x stays, 40 minus x, which is equal to 40x minus x squared. So this is essentially our updated objective function, and that is going to be the equation that we use in order to optimize our rectangle. Okay, so how do we optimize? Remember, we're trying to find a maximum value. So the only way to do that is to find the derivative. So again, what we're going to do is we're going to make this a of x. So it's going to be a prime of x is equal to 40 minus 2x. If we set this equal to 0 to find our critical values, we're going to get 40 equals 2x, x is equal to 20, and this is essentially our critical value or critical points, either way, doesn't matter which way it is, but that's our value. What that also means is that the best possible dimension for our value of x on both sides is 20. That is the optimized value of x. Essentially, if you want to say our width, our optimized width for our problem. Okay, so if we have our optimized width, that means we can also find our optimized length using our y equals 40 minus x. So that's going to be equal to 40 minus 20, which is going to be 20. Okay, so right now, the most ideal situation is for this rectangle to be a what? A square. So they didn't limit. Remember, squares are types of rectangles, so what it's saying is, if I have a rectangle with perimeter 80 centimeters, if I want to optimize the area so that it has the maximum possible area, then I need this thing to be a square. Okay, so once I get these values, so I have this as basically a 20 by 20 square, I need to know what that actual maximized area is. So max area is going to be equal to basically A of 20. You can also do 20 times 20, that's fine, but you can also do this and get 40 times 20 minus 20 squared, which is going to give you 400 centimeters squared. So note these are in centimeters, but that's going to be your result. So it did ask for the dimensions and the maximum possible area, so your answers are 20 by 20 centimeters and 400 centimeters squared. That is the optimization. Okay, so now that we've kind of solved the problem, what I need to just chat about real quick is the interval of interest. So that was the term that's going to be in my math lab, but not super important, I don't think. So interval of interest we got to talk about. So how do we find that? What I said was, all you have to do is take your original equation, which is your A equation right here, this guy, and just set it equal to 0. So if you remember, we set the derivative equal to 0 right here. We're looking for the original equation equal to 0. So if we factor out an x, we're going to get 40 minus x, which means we're going to get x is 0 and x is 40, which means the interval of interest is going to be 0 to 40. So it's going to be 0 to whatever number that is. The reason, usually the first number can't be negative because we're doing measurements. So most of the time the first number is 0. Not every time, but that is usually the case. So if they ask for something like that, then make sure that in the homework, then make sure you're doing that. Okay, so let's pick up the skill level just a tad for this. It says a rancher has 400 feet of fence for constructing a rectangular corral. Interesting. A word that I probably would never use in my lifetime except for reading this problem every semester. It says one side of the corral will be formed by a barn and requires no fence. Okay, so the corral is here. The barn is here. So that means this right here, the corral is up against the barn, and obviously why waste money on fence when that's a sort of a structured fence? So we don't need fence there. There's also, it says 3 exterior fences, so 1, 2, 3. So 1, 2, 3. And then there's 2 interior fences, so 1, 2. So that's what we're going to have to label as we go here when we're doing the actual problem itself. So what are we trying to find? We're trying to find the dimensions of the corral that maximize the enclosed area and the area, whatever that area is itself. So same question as the last problem we have to get through. All right, so how do we put this all together and optimize the area? Well, here we go. We have to look at this and go, we have a setup, right? And we know it has 400 feet of fence. So basically, we need to look at a sum of the amount of fence. That's it. So let's label all the pieces that we know exist. So for example, we can label this as X. But what does that mean also has to be X? Well, that has to be X. If we're dealing with a perfect rectangle, it is. But interestingly enough, so do these have to be X. So we actually have 4 values of X that have to be the same length, 4 pieces of fence. The bottom, though, is an unknown. So the bottom, we're just going to call Y because who knows what that's going to be. Remember, though, we're not dealing with the top, so we're leaving that out. If we were dealing with the top, that also would have been Y. Okay, so I claim we can make our constraint right now because we know that the sum of X, 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 and Y is 400 feet. So what is that? 4x plus y equals 400. Okay, what have we been doing in every problem so far? We've been solving for y, so let's do that now. We're going to get y is equal to 400 minus 4x. Okay, so this is essentially our constraint for our problem. All right, so what else do we need? We need to see what we're maximizing. So again, it looks like area is the key concept. So if I want to find the area of this entire piece of land in the rectangular corral, it's just a rectangle. It's just x times y, just like any other rectangle. It doesn't matter how it's split up. So that means, again, we're a equals x times y. So what do we normally do? We take our constraint, we plug it in. We're going to get x times 400 minus 4x, right? And which is going to give us 400x minus 4x squared. Okay, so we can summarize this as a of x, our true objective function for our problem, is going to be this guy. How do we find our optimization? Well, of course, we take the derivative. So the derivative is going to be 400 minus 8x. We must take this derivative to maximize and set it equal to 0. 400 equal 8x. X is equal to, ta-da, 50. Okay. So what is this value? This is the optimized value of x, and it is the most ideal value for all the vertical fences. If we have those as all 50, that is the best way to maximize the area. And by the way, wouldn't you want to do that? If you were a farmer and you wanted the most possible area, I mean, maybe there's animals in there or something, of course you want that to be the most. So you would do the measurements, you would do this math, and you would figure out that this has to be a length of 50. But what do we need to do? Also, we need to find the value of y. So remember, y is equal to 400 minus 4x. So that's equal to 400 minus 4 times 50. So that means our value of y is going to be 200. So this is all in feet. So that means that the dimensions of our optimized corral will be 50 by 200 feet, which means the maximized area is going to be the product of those, which would in this case be 10,000. But we can also just plug our 50 into our A equation if we wanted to, minus 4 times 50 squared. Okay, we put this in, we're going to get 10,000 square feet. So what are the possible dimensions for getting the most ideal area? 50 by 200. What is that area that we're actually going to get? 10,000 feet squared. So the farmer or whoever's making this can make or rancher can, plan for how many footage they're going to have and so forth. But this is basically what happens sometimes. So let's say you went to a store and you're like, you know what, I got a great deal on 400 feet of fence. So you're like, that's all I'm buying. So I'm going to use that fence the best way I can, and this is the way to do it. Okay, so interval of interest. Just in case for my math lab, make sure you understand. So interval of interest for this problem would be setting this guy right here equal to 0. So we're going to do 400x minus 4x squared, 0. Take a 4x out, get 100 minus x. Solve for x, get x is equal to 0, and x is equal to 100. So our interval of interest would be from 0 to 100, all positive values, and then up to 100. So that would be the possible values of x that you could actually get. Just another sort of a side note here. If for some reason you're ever asked about the connection here, note we're not dealing with graphs on the side or anything with our, that we're doing here. So it's not always easy to see, but in a problem like if they're like, what is the absolute maximum? If that was the straight question, realize that it would just be the point 50 comma 200. So remember, in our first example, when we had the graph, the point is going to be 10 comma 100 because it's x versus whatever your variable over here is. This was product, ours is area, so that would be the absolute maximum. Just to be clear, just in case it comes up at some point. Okay, so last problem. Let's go sort of at a higher skill level, see if we can come up with something neat here. So it says, suppose an airline policy states that all baggage must be box-shaped with a sum of length, width, and height not exceeding 64 inches. Okay, so basically, this is a new airline policy, right? So we're going to assume that this is the case. What are the dimensions of the volume of the square base box, as shown to the right, so this guy, with the greatest volume under these conditions? So again, it's asking for dimensions and greatest volume this time instead of area. All right, so again, what do we need to do? We need to come up with some dimensions on our figure. So there's a key hint here, square base box. So if it's a square base box, why don't we start using different variables just to get everybody used to it? So let's say we do W here and W here because it's a square base box. So essentially, we usually do length times width times height, but the length is also the width if it's a square, all right? And again, let's make this H because that's the height of the box. So right now we have two variables at play within our dimensions. So what is our constraint? It says that the sum of these three variables, here, here, and here, has to be 64 or less. So we don't need an inequality. We can simply just write W plus H is 64, or in other words, 2W plus H is 64. Okay, as we usually do, we usually solve for one of the variables, so we'll do that now. I'm just going to pick the variable that has a 1 in front of it, so I don't have to do a lot of work when it comes to the algebra. So this is basically our constraint. This is what we're limited to in terms of our relationship between the height and the width of the box. That is the key. So moving on. We are trying to optimize volume. So we need a volume formula for this. Well, remember, it's length times width times height. So in this scenario, it's W times H, which is W squared H. So basically, for the scope of what we're doing, we know that we have this set up. Now, what do we normally do next? We take whatever we see here, right? And we put it in for H. So what variable is going to remain? The variable that remains is going to be W. So this is going to be V of W is equal to W squared times 64 minus 2W, which is going to be equal to 64W squared minus 2W cubed. So this is basically our objective function that we are going to start out with, or basically work with is the best way to put it. So this is the earlier one, and then we transform it into this with our constraint. Okay, so what do we do next? As usual, we need to find the derivative of our function. So if we find the derivative of this, we're going to get 128W minus 6W squared. So this is going to be our derivative, and we always set our derivative equal to 0. Okay, well, again, it's a binomial, so we're going to take out a GCF. It looks like 2W, so we're going to get 64, not 54, 64 minus, it looks like 3W is equal to 0, so we set this equal to 0, we set this equal to 0, and we get two results. We get W is 0, and we get W is equal to 64 thirds, which, by the way, is approximately 21.3. All right. So what do we do right away? This is important. So what do we do right away? Is it possible to have a width of this luggage being 0? I hope not, because then we wouldn't have any luggage. So that means this is not possible in the scope of what we're doing, which means our critical value, our key value, is going to be 64. So in order to get this thing, this luggage, box-shaped luggage, to be the most ideal volume, we need the two values of W to essentially be 64 thirds. Okay, so just like last time when we had X, we went back and we found Y. Well, now we have W, so we need to go back and we need to find H. So what do? Just like we've been doing, we do H is equal to 64 minus 2 times W. So it's equal to 64 minus 2 times 64 thirds. If you put this into the calculator and find all the wonderful numbers, believe it or not, you're going to get 64 thirds again as your result. I know that looks bizarre, but just plug this into the calculator and you get 64 thirds. So what does that mean? That means that we also need a height of 64 thirds in order to create a scenario. So what is the most optimized shape of our box? Cube. Kind of makes sense, right? Most optimized rectangles were all squares, so now the most optimized box is going to be a cube. So what are the dimensions? So in order to find our most ideal, what's the measurement of this sucker? Is this in inches? So it's going to be 64 third inches by 64 third inches by 64 third inches. Okay? So this is the ideal dimensions. So what is the actual area? Well, all we have to do is take, these are dimensions. Let me write that. Dim max area. So that's going to be plugging V of 64 thirds. So basically a lot going on here. Do you need to do that? Of course not. You can just multiply these out. But I always give this as an example anyway so that students understand you can find it either way. So 2 times 64 thirds cubed, right? If you find this, what's going to end up, you're going to end up with approximately to 0 decimal places, or with a whole number, you're going to end up with 9,709 inches cubed worth of volume. So this is basically, the standpoint of what we're looking for. We're looking for the most ideal dimensions and the volume that creates. And what's going to happen if the airline policy states that this is what it is? What do you think companies are going to do? They're going to immediately start making cubes out of their luggage because they want to be able to fit the most space into their luggage because customers are going to appreciate that. Okay, and as usual, the last part here, interval of interests. Okay, a little bit different of an equation, but no different in the way you do it. So you got to take your, actually let's do this one. So take that, 64w squared minus 2w cubed, set it equal to 0. Take out a 2w squared, get 32 minus w, so you're going to get w is 0 and 32, which means our interval of interest is 0 to 32, which means in this case our width of this problem, which is our w, can only be between 0 and 32.